Okay. Now look at the next problem. Look at the first three stages of growing pattern of hexagons made using the matchsticks. Okay, now assume that there are three stages. Okay, in book also there are three stages. The first three stages are given. These stage 4 and stage 5 are the stages that I have drawn. Okay, this part is the part of the answer. Okay, don't get confused here. Okay, so assume that there are matchsticks used to form these hexagons. Okay, and they are saying there are hexagon patterns and at every stage the number of matchsticks are getting increased and the pattern is also getting changed at every stage. We have to observe and draw the next two stages. That is what they wanted it here. A new hexagon gets added at every stage, okay, which shares a side with the last hexagon of the previous stage. Okay, now what they are saying is, see, listen to me carefully. At stage 1 there are some sticks used. Okay, and if you see at the stage 2, assuming this is the first, and at the left side of this, see, this is the first one, this is the first one, and at the left side of this it is sharing one of the stick and the next hexagon is drawn. That is what they meant there. Understood this? Okay, and suppose this is the second stage, correct? Now for the third stage, you see that I have the first and second hexagons here. First and second hexagons already were there from the second stage, and at the right side of the first stage there is one more sharing of the matchstick to form the third stage hexagon. You understood this? So the first question in this problem is, draw the next two stages of the pattern. So continuing in this pattern, as I've already explained, we have to draw the next two patterns and find out how many matchsticks will be required at these stages. Okay, now let us find out how many matchsticks were required at every stage here. Okay, first of all, at stage 1, if you count the matchsticks, 1 2 3 6 is the matchstick because it is a hexagon they have already given, right? So it is 1 2 3 4 5 6. Okay, but in stage 2 it is not exactly 6 plus 6 because as they have already explained, one of the matchstick is shared between the two hexagons. So at stage 2 it is 6 plus 5. Only 5 matchsticks are required to draw an additional hexagon. Understood this? Okay, so here it is 6, but it is 6 plus 5 here. Here also 6 is fixed. Okay, let us keep this as 6. The 5 1 was already added, so it is 6 plus 5. Another hexagon is added, so another 5. It is 6 plus 5 plus 5, or you can say 6 plus 5 into 2. 6 plus 5 into 2. This is 6 plus 5 into 1. You understood this? I'm just converting that into a format where I can represent a linear polynomial. Understood this? Okay. Now, similarly, to answer the first question, I have drawn this stage 4. Okay. So, stage 4, you see that this was stage 1. I added the second hexagon in stage 2 and the third hexagon in stage 3. Suppose this is the fourth hexagon added at the fourth stage. It means that there were already 6 plus 5 into 2 hexagons, matchsticks were already used. So if I add one more additional hexagon, how many additional matchsticks are required? 5 only, right? So it is 5 into 3. So here it is 6 plus 5 into 3 required, and here, as you know, this is first one, second one, third one, this is fourth stage, another 5 are required. So this is 6 which are initially required, and then 5 into 4. 5 into 4. At stage 5, I require 4 additional hexagons in which each hexagon is drawn with 5 matchsticks, and 6 were matchsticks required for drawing the initial hexagon at stage 1. Understood this? Okay. So what is the answer for this? First question is, how many matchsticks will be required at these stages? Okay, so I can say as an answer to the first question that at stage At stage 4, what is stage 4 formula is 6 plus 5 into 3, that is 5 into 3 15 plus 6, that is 21 matchsticks. 21 matchsticks. And similarly at stage 5 also they want, right? At stage 5 it is 6 plus 5 into 4 additional hexagons, so it is 20 plus 6, that is 21 matchsticks. Okay, now what is the second part of this? Let us look at this. Okay, now they are saying complete the following table. Now following this, what will be the general form, all that we need to find out, and then finally we have to complete this table. Okay, now let us complete this table, but before that we can answer for the third question using the formula. Using that formula we can easily fill out the table. Okay. Okay, now find a rule to determine the number of matchsticks required for the nth stage. Okay, now we have already seen at stage 1 it is 6, at stage 2 it is 6 plus 5 into 1, at stage 3 it is 6 plus 5 into 2. Continuing in this way, what will be the matchsticks required at nth stage? That is what is required in problem number 3. Understood this? Okay, now let me write that in this way. Let matchsticks at stage 1, matchsticks at stage 1 is equal to 6, correct? Now similarly we know that at stage 2 it is 6 plus 5 into 1. I can say 5 into 1 is 5 only. And then continuing this way, at stage 3 we know that already 6 plus 5 into 2 times, right? So and at 4 we already know that also, that 6 into. So continuing in this way only, you can say that at stage n, you see, when it is stage 1 it is 6, stage 2 it is 1 less than the stage number, you see that, 2 at stage 3, multiplying the last part, you see that the value that is getting varied, keeping 6 plus 5 as the constants in this formula. I can say 6 plus 5 is kept as it is only, but at nth stage it is n minus 1, because at fourth stage it is 3, at third stage it is 2. You understood this? Okay, I can say this as 5 into n minus 1. Understood this? Okay, now let us resolve this equation by multiplying 5 into n minus 1, and finally find out the linear polynomial that represents n. Okay, so I'm doing it here only. Okay, listen to me carefully. I'm just taking this to the next stage, and that is n. Okay, or I can say the value of n. Okay, they want a matrix, right? So I can say m of n. Okay, m of n is equal to 6 plus 5, 6 plus 5 multiplied by n minus 1. Okay, now let us multiply 5 to both n minus 1. It will be 5n minus 5. Okay, 6 minus 5, it is 1. So therefore m of n is equal to 5n minus 5n 6 minus 5, that is 1 plus 1. Okay, so it is 5n plus 1. Using this only I can substitute this table. Okay, yeah, of course you would have substituted that by this part also, but you can easily substitute by this formula. Okay, now let us try substituting this. N is equal to 1, it means n is equal to 1 here. If you substitute n is equal to 1, 5 into 1 plus 1, that is 6. Okay, at stage 1 we have 6 matchsticks. Okay, at stage 2 it is 5 into 2, 10 plus 1, 11, correct? It was 6 plus 5. Understood this? Okay, 5 substitute 3, 5 into 3, 15 plus 1, that is 16. 4 15 sorry 5 into 4, that is 20 plus 1 21. So at every stage actually 5 is getting added here. That's all. 5 matchsticks are getting added. So finally at nth stage it is 5n plus 1 according to whatever we have found out. Understood this? Okay. Okay. Okay, now let us move to the next part. Okay, there are two more parts of problem number 12 itself. How many matchsticks will be required for the 15th stage of the pattern? Okay, now we have the formula for matchsticks. M of n is equal to 5n plus 1. Using that only, let us substitute n is equal to 15 in that. You're going to get that. Okay, so I can say we know that m of n is equal to, m of n is matchsticks at stage n. Okay, m of n is equal to 5n plus 1, and here given is n is equal to 15. That is the 15th stage. Okay, so therefore m of n is equal to, m of n is equal to 5 into 15 plus 1, that is 15 5s are 75. Okay, plus 1, that is 76 matchsticks are required at stage 15. Understood this? Now look at the fifth part of this question, that is, can 200 matchsticks form a stage in this pattern? Justify your answer. Okay, now looking into this problem, listen to me carefully. It's very, very important that they are asking 200 matchsticks whether they can form a pattern of this kind or not. First of all, if you have 200 matchsticks and you have to find out the stage where 200 matchsticks can form this pattern, it means that the value of n you should be finding out given m of n is equal to 200. You understood this? Okay, so substituting m of n is equal to 200, if n value if I get as a positive integer, because n represents a stage number, right? So you should always get n is equal to a positive number, positive integer, then only you are going to say that 200 matchsticks can form a pattern of this kind. If you don't get that value as a positive integer, okay, then there is no stage where 200 matchsticks can form this pattern. That is what our conclusion should be. You understood this? Okay, let us find out that. So I can say here m of n is equal to 200. So total matchsticks they have given, right? M of n represents matchstick, right? So here I can say here m of n is equal to 200, and we need to find out n value. That is the stage where 200 matchsticks can give me this pattern. You understood this? Now let us substitute m of n is equal to 200 into this formula and try to find out the value of n. Now let me write the right side value first here. 5n plus 1 is equal to m of n, that is equal to 200. Okay, I've just swapped the left and right because the value of left side is already given as 200. Okay, keeping 5n to the left side, I will take 1 to the right side, that will be 200 minus 1. Okay, so that will be equal to n is equal to 200 minus 1, that is 199 divided by 5. Okay, is 199 fully divided by 5? Okay, 199 I cannot divide 199 fully by 5 getting a positive integer only. If it would have been 200, it will be fully divided by 5. Okay, so therefore I have to justify my answer, right? So I didn't get any, whatever may be the value of n, you are not going to get a positive integer. It is going to be a fraction. It is going to be a fraction. Okay, so therefore to justify my answer I can say, therefore since n is not a positive integer, it can't represent a stage in this pattern. It can't represent a stage in this pattern. Represent a stage in this pattern. In this pattern. Understood? Okay. So therefore, so 200 matchsticks cannot form a in this pattern. So in this pattern, 200 matchsticks, using 200 matchsticks, we cannot form any stage. Understood this? Okay. Let us quickly move to the next problem. Okay, now problem number 13 also is given with two of the polynomials ax plus b and cx plus d. Okay, we have seen one of such problem previously also. Okay, be two linear polynomials such that there are some conditions given such that the graph of p of x passes through 2 points 2 3 and 6 11. Okay, using that two coordinate points we can find out p of x. Okay, similarly the graph of q of x passes through the point 4 minus 1. They have given one condition that q of x passes through 4 minus 1. It means that if x is equal to 4, y is equal to minus 1. Y in this case is q of x. Okay, so here in this both the polynomials, whenever I say y is either p of x or q of x in these two polynomials. And finally there is one more condition given, the graph of q of x is parallel to the graph of p of x. Okay, this is very important. How do we make use of this point is a very important discussion. Okay, let me make use of these two and first of all find out the polynomial p of x, then we will finally find out the value of q of x. So finally what we want is we have to find out both the polynomials and also find the coordinates of the point where these lines meet the x-axis. Given point 1, given with point 1, what I can say, x is equal to, or you can say for x is equal to 2, for x is equal to 2, p of x or y is equal to 3, right? So I can say p of x is equal to 3. Okay, let us substitute that here in this equation. What I'll go, I'm going to get 3. Sorry, x is equal to 2. That is 2a plus b is equal to 3. Therefore, 2a plus b, 2a plus b, and p of x is equal to 3 in that case. Okay, this is equation 1 from the coordinate point 2 3. You understood this? Okay, now similarly and for x is equal to 6, p of x is equal to 11. P of x is y in this case, don't get confused. Okay, so let me take the second coordinate and form the second linear equation, that is for x is equal to 6, p of x is equal to p of x is equal to 11. So therefore I can substitute x in place of this formula, x is equal to 6, so that is 6a plus b. Therefore 6a plus b is equal to 11 is my second equation. So I can say subtract equation 1 from equation 2, that is equation 2 minus equation 1. So write the left side of the equation 2 first. 6a plus b minus of 2a minus of b. So I can directly write it as minus 2a minus b. Okay, you are multiplying minus to both the terms of the left side. Okay, so that one step I have skipped. Okay, 11 minus 3 on the right side, 11 minus 3 on the right side. B will get cancelled. For 6a minus 2a, that is 4a. 4a is equal to 11 minus 3, that is 8. So that is a is equal to 8 by 4, that is equal to 2. Okay, so a is equal to 2. One value from this a we got it. So now if I substitute the value of a 2 in place of equation 1, I can get the value of b. Okay, or in any one of these equations you can substitute, you are going to get the similar value. Okay, now substitute in equation 1. So therefore from 1 I can say, from equation 1, b is equal to 3 minus 2a. Okay, b is equal to 3 minus 2a. Okay, I'm taking 2 to that side. B is equal to 3 minus 2a. Let us substitute the value of 3, sorry, a, that is 2. Okay, so therefore b is equal to minus 1, right? 3 minus 4, that is b is equal to minus 1. So I got the value of a as 2, b as minus 1. Substitute in this, that is 2x minus 1 is equal to p of x. Okay, so therefore the polynomial, the required polynomial p of x, well, I can get it by substituting a is equal to 2 and b is equal to minus 1 in this. Okay, so that is p of x is equal to ax. What is the value of a? Is 2, so that is 2x. And what is the value of b? That is minus 1, so it is 2x minus 1. 2x minus 1. So this is the first polynomial that is required from this question. Okay, so the second polynomial, now to get the second polynomial we have to make use of the second point. The graph of q of x passes through the point 4 minus 1. Okay, now before that you can make use of this. The graph of q of x is parallel to the graph of p of x. If the graphs of the two lines are parallel to each other, then we know that their slopes are equal. Okay, so in this equation or the polynomial, 2x minus 1, 2 is the slope here, you know that, right? It is ax plus b. Okay, always in this ax plus b, a is called as slope and b is y-intercept. So here slope is equal to 2. Slope of p of x is 2, right? That is c. C is slope of q of x here, right? C is the slope of q of x. So c is equal to a and that is equal to 2. Okay, so that I can write it as 2x plus d. Now let us continue and make use of the point 3. Okay, okay, so from 3 I can say, from 3 what they are saying here is, what they are saying is slope of p of x, slope of p of x is equal to slope of q of x, right? Slope of q of x, that is a is equal to p of x is a and slope of q of x is c, that is a is equal to c, but we know the value of a already, that is equal to 2. Okay, so therefore c is equal to also 2. So if I substitute c is equal to 2 here, what this equation will become? Q of x is equal to 2x plus d. Okay, so therefore q of x is equal to 2, c is equal to 2, right? 2x plus d, right? Okay, now we have actually reduced the value of q of x to 2x plus d, and we now only have d constant d to be found out to equate this q of x equation to linear polynomial. Okay, now what is given? Point number 2. Point number 2 says q of x passes through the point 4 minus 1. It means that if x is equal, for x is equal to 4, y is equal to minus 1, or q of x is equal to minus 1. So I can say from point number 2, from point number 2, for x is equal to 4, for x is equal to 4, I'm making use of this point. Okay, I'm making use of this point 4 minus 1. For x is equal to 4, q of x, because they are saying q of x passes through that point 4 minus 1, I can say q of x is equal to minus 1, that is y is equal to minus 1. Okay, so therefore substitute that minus 1 here in this place and x is equal to 4 here, so that will be 2 into 4 plus d is equal to minus 1, right? Q of x is equal to minus 1. I'm just substituting that. So 2 into 4 is 8. Taking 8 to that side will make it d is equal to minus 1 minus 8, and therefore d is equal to minus 9. D is equal to minus 9. Substituting d is equal to minus 9 in this equation, therefore I can say q of x is equal to 2x minus 9. 2x minus 9 is the second required polynomial. Understood this? Okay. Now the next part of this question. Now we have completed this. Find the polynomials p of x and q of x. Now the next part of this is find the coordinates of the point where these lines meet the x-axis. Okay, that is very important. So we have to say that finally I can write it as finally p of x and q of x at y is equal to 0. Okay, or you can say p of x is equal to q of x is equal to 0, both equal to 0. It means that I can say 0 is equal to 2x minus 1 is the p of x. Okay, so 2x is equal to so minus 1, I will take it to the left side. That will give me 2x is equal to 1, right? Minus 1 taking to the left side, so x is equal to half. So x is equal to 1 by 2. Okay, so the coordinate point where therefore uh, 0 sorry x is equal to half, x is equal to half and y is equal to 0 is the coordinate point, is the point where p of x intersects x-axis. Okay, or cuts x-axis. Understood this? Similarly, I can substitute y is equal to 0 or q of x is equal to 0 in this equation. I can say similarly, and 2x minus 9 is equal to 0. Okay, or else, okay, now if you are getting confused, let me give the name to this equation 2. This is from equation 2 and this is my equation 1. This is my equation 1, so that where you are substituting you should be getting that right. So why this is taken, because from 1 I can write it as from 1. So please write it here as from equation 1. From equation 1 you got this. Okay, this also I will write it here as from equation 2. Okay, so that there is no confusion. You understood this, right? Okay, so this 2x minus 9 is equal to 0 I considered. So therefore x is equal to minus 9, I will take it to the right side, and 2 to the right side. Again 2, a multiplication will go into the division, and x is equal to 4.5. Okay, so what is the next coordinate then? So the coordinate point, therefore the coordinate point 4.5 and 0 is another coordinate point where q of x cuts the x-axis. Okay, where q of x cuts the x-axis. Hope you understood this. Okay, now if you plot the graph, okay, let me see whether I have plotted the graph for that. Okay, see, I have plotted the graph for 2x minus 1 and 2x minus 9. Okay, this is not part of the question, but for the verification purpose I've just plotted it. If you want you can take it down, or this is not a part of the question. Okay, so just for verification I did this. Okay, now let us check whether 0.5, that is half, 0 is one coordinate point where 2x minus 1 cuts the x-axis. You see, I've taken some random points, 2, 3 for the first line. 2, 3 is this first coordinate point. Okay, and then 6, 11. 6, 11 is this coordinate point. Okay, this is 10 and this is 11. And if you draw the line and extend that line, you see that this is cutting the x-axis at half, right? 0.5 and y is equal to 0. Is it cutting this? Okay, and that is what we have found out by uh, theoretically also. You see that 1 by 2 0, where this equation 2x minus 1 cuts the x-axis. You see that it is cutting it. Understood? So that similarly, randomly I have taken it for 2x minus 9 also. 4 minus 1. 4 minus 1 is 1 point. So this is 4 minus 1. It means that if you substitute 4 here, you will get y is equal to minus 1. For 1, it is minus 7. So 4 minus 1 is 1 point. And for 1, it is minus 7, another point. And if I just uh, draw the line and extend it for what is the point, that is 4.5, it is y is equal to 0. Where does it is cutting the x-axis? Where does it is cutting the x-axis? It is here. You see that it is between 4 and 5. It is 4.5, 4.5 and 0. It is cutting the x-axis. So this line is the second line and this is the first line. So graphically also we verified that those two are the coordinate points where these two lines correspondingly or respectively cutting the x-axis. Understood? Understood this, right? Okay. Now let us see the last problem in this. Okay. This is a very, very simple problem. What do all linear functions of the form f of x is equal to ax plus a? See here the slope and the y-intercept are same only. Given the condition a is greater than 0, have in common. Okay. So it is a general form of a linear equation where slope and y-intercept are equal, given that a greater than 0. If you draw different lines by taking different values of a and x, if you draw such lines, what those lines will have in common? That is what the question here is. You understood this, right? Okay. Now let me take this equation first. F of x is equal to ax plus a. Now, as a is looking common in both these terms, I can take common as a and I can write it as x plus 1 or a multiplied by x plus 1. Correct? Okay. So, I can just modify the function f of x as a and x plus 1. So, if you equate this to a linear polynomial, it becomes ax where x is x plus 1 only and equal to 0, and this is y-intercept, right, equal to 0. So there is no term b here in this in common, and this is y-intercept. So if there is no y-intercept for any value of a, because they have given it as a greater than 0, okay, I can equate this equation to 0 where it cuts the x-axis. Where it cuts the x-axis, I can find out the generic value. Okay, so I can say, since given as a greater than 0, since a greater than 0, a is greater than 0 given, that is given. So it means that a is going to be always greater than 0. I can equate this a x plus 1, a x plus 1 equal to 0, equal to 0. I'm putting y is equal to 0. Okay. So I can say let y is equal to 0, let y is equal to 0, or y is nothing but f of x. Okay, in this case f of x, let y is equal to 0. I'm substituting that. So since a is greater than 0, I can take a to the right side and it will become 0 only, and x plus 1 is equal to a 0 by a. Okay, 0 by a is equal to 0, that is x is equal to minus 1. X is equal to minus 1. Understood this? So all these lines, what they have in common is, if you put a y is equal to 0, it means that you are trying to find out the coordinate point where all these lines cut the x-axis. At what point they cut the x-axis is minus 1, 0. Minus 1, 0. So that is one common thing that they have in all these lines. Therefore, all these lines cut the x-axis at x is equal to We found out the value -1 and 0. This is one common point that is there. And what is the other common point is, since they have given a greater than 0, what is a in this case? What is a in this case? In the reduced formula, you check what is a. It is slope. So slope into variable plus y-intercept. Y-intercept is 0 only, and I can say slope is greater than 0. So if you have slope as greater than 0, it always has a positive slope and is in the increasing mode. That is one common point in all these lines. Understood this, right? I can say since a is greater than 0, a is greater than 0, we can say right, positive slopes and in increasing mode. That is the second common point. You can just write as common points and then list out all these points. Okay, that is what the question here. That's why I'm writing it in a descriptive way. Okay, now what is the other common point is y-intercept in all such lines is 0, because there is no y-intercept given. There is a common slope that is given here. Okay, so I can say that. And also y-intercept, you can see that here itself. Okay, y-intercept is 0 because it always cuts the x-axis at -1. Okay, and I can say y-intercept in all such lines is 0. Okay, so that is what the last common point that you can observe. Understood this? Okay, so now this completes problem number 14, and this completes all the problems from end of chapter exercises. Okay, now let us quickly look at the chapter summary and end the chapter. Okay, now whatever we have studied from the beginning of this chapter. Okay, now we started with an algebraic expression that represents the polynomial in general, not a linear polynomial in general, and what are the parts of that polynomial. Okay, it combines the numbers, variables, and operation symbols. Here in the example, if you see, variables are x, and y, xy here. Okay, and variable, okay, numbers are these coefficients 2, 5, and constants also. Operation symbols are plus and minus. Okay, that is what the simple explanation. Now next comes the algebraic expression combines the numbers, variables, and operation symbols to form this polynomial. This is polynomial in general. Okay, combining all that we have formed this. And finally we came to the specific part of this chapter, that is linear polynomial or univariate polynomial, are the algebraic expressions in one variable. Here in this expression we have two variables x and y, but such variables or such expressions in which only one variable exists, those kind of expressions or algebraic expressions are called as univariate expressions, univariate polynomials you can call. Okay, here it is a polynomial where only one variable x is there, so that is a univariate. We are actually nearing to the definition of a linear polynomial, okay, while discussing it. Now next comes the degree of the polynomial. Okay, you remember that, right? uh, Inside, specifically in a univariate polynomial, the highest power of that variable in which that equation is defined, the highest power is called as degree. So in this equation the degree of the polynomial is 2 because the x variable has the highest power as 2. So that is what the definition. Highest power of the variable in a univariate polynomial, specifically in univariate, okay, not in a polynomial with two variables, it is called as degree. And example here given is x square plus 5x plus 3, the similar example only. The degree is 2, and in this it is a y polynomial. Okay, polynomial in y, the degree is 3 here because the highest power of y, okay, is 3 in that case. Okay, now what is linear polynomial specifically is polynomial of degree 1. Okay, there first of all it is a univariate polynomial, and the highest power of that variable should be 1 in that case. Such polynomial is called as linear polynomial, and that is a point of discussion in this chapter. Okay, we are dealing with only such polynomials wherein the highest power of only single variable existing in that has 1 as the degree. Okay, so example of such linear polynomials are 2x plus 3, 5 minus 4y. Okay, here it is x variable, here it is y variable, but if you see the polynomials, the degree of that polynomial, it is 1 only. Okay, are the linear polynomials in x and y respectively. And finally we have discussed some points like linear patterns and how to draw that, how does the linear patterns represent linear polynomials, all that we have discussed. And in that linear growth also, linear decay also we discussed. If you remember, you know the difference of between the growth and decay. If there is a constant increase in the whole value of the expression with a change in value of x and y here, then that is called as growth. If there is a value constant decrease in the value of the whole polynomial with the change in value of the variable, that is called as decay. Okay, if you don't remember, please watch the previous videos. You will come to know we have a specific video done on linear growth and linear decay. Watch that video for the explanation. And finally we have a specific video on linear relationship also. Okay, what is the relationship between the two variables x and y? Okay, now if you consider y is equal to ax plus b as the generic form of the linear polynomial, what is the relationship between x and y? That defines the relationship. Okay, linear relationship, we have a specific video on that also. Okay, represented by a straight line, y is equal to ax plus b, where a is called as slope of this line. Okay, we have discussed this also. And then constant b is called as y intercept. Okay, so this is all a simple summary of this chapter what we have studied. Okay, so this completes the second chapter, introduction to linear polynomials. Okay, let us meet in the next session with a new chapter, chapter 3, world of numbers. Okay, thank you.